Okay, the triple product is yet another product, and you can guess by its name that it's going to be involving three vectors. We're going to call them, ready? A, B, and C. Ha. But the definition of it is not going to be something new. It's actually going to be based on two previous products that we've seen. So the triple product of A, B, and C, here's A, B, and C. You take B and C, you do the cross product, and then you take A and dot it with it. That's the triple product. Okay? Now, what kind of animal is this? It's a scalar, right? Because B cross C is a vector, and then the dot product of two vectors is a scalar. Do you agree? So this is a scalar. Okay, and I'm going to right away write a theorem which kind of summarizes the important properties of this thing. And I'm not going to prove all of it, but I'm going to explain parts of it. So part one says that the triple product of A, B, and C equals, now I'm right away going to write the short notation for it, which is going to be using this determinant. And you just write the components in the three rows. A1, A2, A3, B1, B2, B3, and C1, C2, C3. So what's the claim here? And I'm going to leave it to you to prove it. It's just a bit tedious of a calculation to show that this is true. Okay? So you need to first do B cross C. You know how to do B cross C. Take the result, dot it with A. You know how to do that. And you're going to get some expression involving the components. Okay? And you have to check that that expression is precisely what you get over here. What do you get over here? Look up here for a second. I'm just going to show you. So it's A1 times B2C3 minus B3C2 minus A2 times B1C3 minus B3C1 plus A3 times B1C2 minus B2C1. Do you agree that this is just a short way of expressing a long expression? Okay? It's more than that. It's a determinant, and you're going to be discussing determinants in length in the algebra course. But for us, it's just notation. Clear? Okay, so prove this. Homework. Show that this is true. It's not hard. There's nothing tricky there. It's just spelling out the entire thing, and it becomes... I mean, I just told you what you're going to get on this side, so you're probably going to get that on the left-hand side as well. Okay? Okay, part two. So this is kind of a weird property. So if you take A dot B cross C, that's the triple product, and you try to think what kind of properties hold for it, so the property that holds is this sort of cyclic property, namely that A dot B cross C is the same as B dot C cross A, and this is in turn the same as C dot A cross B. Okay? Now one way of proving this is spelling everything out. That's the long way of proving it. The short way of proving it is building up on a property of matrices that you don't know yet because you don't know matrices yet. But that property, which you're going to meet, says that if you take two rows of a matrix and change them, just interchange them, right? The third row as second and the second row as third, the determinant, the expression that we got, this times, this times, this minus, this time, right, is going to be different is going to be different, but it's not going to be completely different. It's only going to change by a minus. Okay? And that requires proof. It's not hard. But if you think now what's written here, A dot B cross C is writing the row corresponding to A first, the row corresponding to B second, and the row corresponding to C third. Right? What is B dot C cross A? Well, you're writing B second, C third, sorry, B first, C second, and A third. Okay? So how do you get this from this, or vice versa? Well, if you replace A and B, you get B first where you wanted it, right? And A here. And now if you replace A and C, remember A is now here, you get exactly the determinant corresponding to this. Do you see that? So in order to get from here to here, you replace once 2 rows, you just threw in a minus sign, and then you replace another 2 rows, you throw in another minus sign. Minus minus is plus. So that's the short proof of this statement. Follows immediately for properties of determinants, which I just told you. Clear? Good? Okay, so that's the idea of the proof of this. And the third property is the geometric meaning of this triple product. And that's kind of the reason that it shows up. And that I want to discuss a bit more. I want to prove that. So it says that A, B, and C, these 3 vectors, are, so here's a word that we haven't seen yet, coplanar. What does it mean that they're coplanar? It means that they're on the same plane. So if you take through 3 vectors, here are 3 vectors, in general they're not on the same plane. Do you agree? In general, they don't share a plane, right? It's kind of something unique for 3 vectors to be on the same plane in general, right? These 3 vectors are on the same plane. Do you see that? But when you take any 3, there's no reason for them to be on the same plane. Any 2 are on the same plane, but not all 3. Do you agree? So if you take 3 vectors, they will be coplanar if and only if their triple product, A dot B cross C, is 0. So this is kind of a way of checking if 3 vectors are coplanar. And if they are coplanar, it's something that you usually want to know. And if you don't encounter them geometrically, if they're given in coordinates, for example, how do you know if they're coplanar or not? If you have the vector 1, 2, 17, pi minus 5, 6, and 1/3, 1/4, negative 5. How do you know if they're coplanar or not? Okay, you plug them into this and check if you get 0. Clear? I want to show you why this is true. Okay, so we explained this. This is just a calculation. We explained this. It follows from a property of determinants. And this I want to prove. So why is 3 true? So 3 follows from the following observation. And the observation is the geometric meaning of the triple product. So when you have 3 vectors, and now you're gonna need again to a bit focus and relate to my three-dimensional attempts to draw pictures. So here's the vector A, and here's a vector B. So far it looks rather 2-dimensional, right? And I'm going to take a third vector C, and C I don't want it to be on the same plane. I want it to be on a different plane, right? Just any general 3 vectors. So I'm going to draw C as going into the board, like this. So this This is C. Okay, and you should imagine it as going into the board. Okay? Just like any two vectors give you a parallelogram, the three vectors give you something that looks like a box, but each side of which is a parallelogram rather than a rectangle. Do you know what that is called? Right, a parallelepiped, and there's no chance that I'm going to try writing that. So here goes. I'm going to draw it. So, and when I draw dotted lines, it means they're in the background. They're hiding behind something. So I can complete this into a parallelogram. There it is. Right? This is in front of us. And then, so this is a copy of B, and this is a copy of A. Right? And now I can draw here a copy of C, like this, and another copy of C here, like this, and another copy of C here, like this, and here's another copy of A, and here's another copy of B. Missed. Okay? And then there's the ones in the background. That's why I'm drawing them as dotted. Okay, so do you agree that this is a parallelepiped? Good? Okay. Now, what's the volume of this thing? Not the area, the volume. It's a three-dimensional object. Okay? So, and do you agree that three vectors give you a parallelepiped? Right? Okay, so the volume of this thing equals, so how do you do volume of a thing like this? You need let's write it in words first. So you need the area of the base, times the height. Do you agree? Do you agree that that would be the volume? Okay. So we don't have a height here. The base is just the parallelogram based on B and C, right? That's the base. We don't have a height yet, but I'm going to draw one. So I'm going to take this corner and drop a line which is precisely perpendicular to the base. Okay, so let's dot this, and there's a 90-degree angle here. Okay, and this is going to be H. Do you agree? Good? So now I'm going to write the volume of this thing is what? What's the area of the base? What's the area of the base, which is a parallelogram based on B and C? Right, the absolute value of B cross C, that we discussed previously. Do you agree? Times H. H is just a number for now. So do you agree so far? Okay, now what is H? Let's think for a minute. So let's call this angle here, so this is a right triangle comprised of A, H, and whatever this little line here is. Okay, it's a right triangle. And I'm going to call this angle up here alpha. Okay? Good? Now, do you agree, here's the little tricky part, that if I were to take B cross C, what is B cross C? I need to take my fingers, point from B to C, and then my thumb is pointing in the direction of B cross C. So do you agree that B cross C is exactly in the direction of this H height? Do you agree? Okay, exactly. But if B starts here and C starts here, to be consistent with our previous, wait, A is a vector. To be consistent with the way we drew things previously, then B cross C, I would need to draw something like this. This is B cross C. Do you agree? Everybody? Now, do you agree, from basic geometry, so B cross C, and, well, A is now in the way. This was A. This. Do you agree from basic geometry that since B cross C and H are parallel, this angle here, alpha, and this angle here, alpha, are the same? Good, everybody? Okay, maybe I'll draw this here a bit bigger. So this is B cross C. This is A. And this is the line H that we drew, right? And this is a right angle here. So this alpha and this alpha are the same angle. Do you agree? So the angle alpha is the angle alpha between A and H is the same angle as the angle between A and B cross C. Do you agree? Everybody? Good? Okay. Now, let's try to figure out what H is in this right triangle. The cosine of alpha equals H over the length of A. Do you agree in this right triangle? Everybody? So what is H? It's the length of A cosine alpha. I'm going to replace that here. So it's B cross C times the length of A times cosine alpha. Do you agree? And what we got here is precisely the dot product of A and B cross C. It's A times B cross C, lengths, times cosine of the angle between them, because we agreed that this is the angle between them. So this is precisely A dot B cross C. Do you agree? Everybody? Okay. Well, just one little tiny correction. Yeah, if we want to be completely precise, we need to take the absolute value of this, because otherwise we might get negative. Here we could get a negative number. Okay, not in this picture, but in general. Okay, so what we want to say is that let's just put it in absolute value. And I'll put the cosine in absolute value. That's what could introduce the minus. Okay, clear? Okay, so what was this remark? Okay, so the volume of the parallelepiped is exactly the absolute value of the triple product. Do you agree to that? Okay, so let's write it. Volume of P equals the absolute value of the triple product, A dot B cross C. That's the geometry. When can this volume be zero? Can a volume of a parallelepiped ever be zero? Only if it's a parallelepiped which was very unfortunate and somebody stepped on it and made it flat. What does it mean made it flat? That these three vectors on which we built the parallelepiped were originally in the same plane. Then the parallelepiped is a fake one. It's just a projection of one, a flat one. Do you agree? Okay, so it follows from this, hence 3. 3 was the theorem that this is 0 if and only if this is 0, which can only happen if A, B, and C are coplanar. They're on the same plane. Do you agree? Everybody? Questions? Good? You're quiet. Is that because everybody is with me? Okay, good. So, I guess we'll stop here with this. All of what we did so far was kind of introduction to vectors. What we want to do now is in the next few lectures, is to start understanding three-dimensional space. We understand two-dimensional space pretty well, right? That's kind of what you did in Calc 1. For example, what is a line in two-dimensional space? You know how to express one as an equation, right? Y equals ax plus b, right? You know how to express even more complicated things like a parabola, y equals x squared, right? Or even more complicated things. And if you want to do multivariable calculus, we're going to want to deal with three-dimensional space. What is a line in three-dimensional space? What is its equation? I mean, do you agree that it perfectly makes sense to talk about a line in three-dimensional space, right? What's the equation of a line? We have to figure that out. In three-dimensional space, we can talk about a plane in three-dimensional space. What's the equation of a plane? And of course, more difficult objects. For example, not a parabola, but a paraboloid. A paraboloid is kind of a 3D parabola. That's called a paraboloid. Or, well, if you take a circle, what do you call it's not called a circloid. What do you call a ball? A sphere, right? That's the three-dimensional version of a circle. Okay? What do you call a three-dimensional version of an ellipse? Ellipsoid. Okay? And those are the simplest objects. Those are kind of objects that are quadratic in their equations. And they're going to be. They're just going to have three variables in them. Okay? And we're going to somehow want to figure out more to get feeling more friendly and cozy with three-dimensional space. So that's coming up next.